Hello, everyone. Thanks for being here. I know there is a lot of good talks, competition with us, so thank you for being here. Today we're going to talk about, well, since it's after lunch, it's very suitable to talk about gravity and data gravity and how to overcome it, which is in some ways the how do you deal with data in a microservice universe, which is not an easy subject, as we will see. So today we're going to give you options. So it's really here to try and open your minds, to try and see about various options you could think about. We do not claim that this is the perfect answer and you have to go for that, and that's the stuff that works everywhere. So my name is Emmanuel Bernard. I work at Red Hat as a chief architect for everything data inside the middleware. Historically on Hibernate and still there and so on.
And hello, my name is Madou Coulibaly. I'm a solution architect specialized on the data and cloud native development at Red Hat too.
Cloud native. Right. So I won't give you the, hey, microservices is great. We all know. Who is actually doing it for real? Okay. So, you know, it can be painful, right? And suffering. So I won't claim this is not the case, but let's remember why we're doing it. And for me, there are two big things. The first one is to really be able to say, I can get a small team with a super high velocity to really focus on one area and be able to deliver. My time to delivery should be as fast as possible. So it doesn't mean that my throughput is going to be faster on deliver as many features as possible. This is not what's happening. What's happening is that I'll be able to deliver the one feature I really need to get to market much faster because I won't be encumbered by with other areas. The other one is more technical, the ability to decide which very specific part of my system do I need to spend a lot of energy to scale up, down, you know, versus the rest, which is, you know, less used. And you need to have a very fluid infrastructure to, you know, really get double down on the benefits of microservices. You know, the hype of the days is really, you know, containers and Kubernetes as a very fluid way to be able to deploy things. And, you know, this is really a fit, which is pretty good. Yes. So unless you're a startup starting like today with zero data and like everything like a blank page, in real life, at the very least, you have existing data. So I'll call that a brownfield database as opposed to greenfield, right? So it's a brownfield database with lots of data. And of course, when you write a greenfield service, you will have to use this existing data to be in any way, shape, or form useful. Okay, and while we can use the strangle the monolith approach to really say I'm going to write this microservice on the side that will slowly replace feature after feature whatever my monolith application is doing, the data remains something to deal with. So remember, you used to have this one big application, and now it's, I don't know, 20 microservices. And the key is that each of those microservices that I not very smartly called apps here, actually should have a very independent life cycle from one another. So if I really have to deliver something on app 3, then the fact that app 1 is nowhere near ready for the next delivery is not a problem, right? So the life cycle and the teams can really focus on wherever it makes sense. But the data, I mean, when you split your data, your application, your big application into 20 bits, you will realize that the same data is actually used across those 20 subset of the applications, right? A user is a user after all, right? It's not like it's being transformed and totally isolated. And sometimes you want a user with a little bit of order and whatnot, right? So it's always a bit complicated to split that. So you could say, hey, I'm keeping my existing database and I'll use my microservices and they will be able to release in an independent lifecycle and life is good. Not quite. Because when you think about it, first of all, the fact that your application could access the actual schema and say, no, I swear I will only use the user table because that's my bounded context, right? But it's so easy to do just one extra join to just get, say, the total number of orders for that user. And then just yet another table, just this one time, right? And you end up having each application accessing the whole data or 80% of the data. And Every time you do a schema change, you don't have to just think about app 2 doing the schema change, but all of the other applications actually also interacting with the same table or the same column and whatnot. The other problem, which is a bit more subtle, is, all right, I need to optimize application 2, and I found the best solution. If I put this index and that index on the database, it's going to be 5 times faster. Awesome. Except, it turned out that this extra index is having a lot of impact on application 3, and now it's 100% time slower. So you see that the whole isolation and being able to do changes without impacting the rest of the people is actually a lie when you have the same database underneath. So if you look at the literature, and Martin Fowler sort of captured that, the perfect solution, or at least the end of the journey, is something that looks like that. The way I like to describe it is to say you need islands of microservices, and each microservice is an island that contains the code you execute to actually do something and the data itself. And code plus data lives in one island, and this island has the life cycle, decide when it releases, what technology it uses, whether it needs to release right now or in 3 months, right? But of course, a user being a user, you need to be able to share that state between the other applications, the other microservices. And the way you do that is to define bridges between those islands. And you can use various techniques. Data stream is a very interesting and popular technique where you literally send any kind of modification events to your buddies, so any change events that can be consumed by the other downstream microservices and then deal with it in its own way, right? So you need to have a super clear contract. It's not like, hey, I'm sending JSON strings and life is awesome. No, you need to have a schema because that's really your contract. Just like when a microservice call another microservice with a well-defined REST API that you shouldn't break, it's the same logic for the data changes. The schema is important. That's your contract. It could be data copy, frankly, like an ETL-based thing, as long as you really understand and agree on the contract between A and B. But that's kind of a big bang situation because, first of all, my monolith application will no longer be able to work in this universe because instead of one big monolith database that the application was relying on, the data has been split into, in this case, 4 different pieces. So that's a big bang in the sense that I cannot keep the monolith running while having those changes. So a bit of a trouble here. Yes, and the other problem is the bounded context. So the isolation between one microservice and another is really hard to define. I don't know if you guys are following bounded context, but you go with one and then you realize, you know what, we messed it up. It really should, this part should be there or partly there or duplicated and this part should be there. So being able to define those microservices from the get-go is actually definitely a non-trivial problem. So one option we do discuss today is this notion of data virtualization. So there is a project named TEID, which is impronounceable, but you can read it, TEIID.org. And the key is to say, from a microservice point of view, I will go and access this database, which happens to be a virtual database, but who cares? Because I'm using a JDBC driver and I'm connecting to a socket, which is this virtual database server. And from all intended purposes, I'm doing SQL queries to read, update, delete, and do everything I do with my database. So you got this virtual database layer, which has a schema, a notion of a schema, which we call logical schema. And that schema is logical in the sense that there is no data in this virtual database. The data is actually in a physical database, in this case, the monolith database. And what happens is from the logical schema, we do a conversion to the physical schema of the monolith database. So we take the SQL, we convert it into the right SQL, go do the query, and send it back. So in many ways, it is just a proxy, except it can filter and really show exactly what the monolith application need or should use. Okay, so no data is copied, and by the way, it's read-write, so I can read stuff from there, I can write stuff, it just works. So what are the benefits? So first of all, the monolith still works because we haven't moved the data, so that's a very big benefit. I can start to shape my bounded context by defining my microservice, defining this virtual schema on the virtual database server, and saying, oh no, I only use the user table. And when the team says, you know what, I also need this other order information, then you can have a conversation with the other team and try to say, okay, who owns that and what happens. So you have clear boundaries on that. These are virtual nevertheless, so you can really decide, you know what, it was a bad decision to only do this subset, so let's extend or reduce, the virtual model here, and then you adjust the microservice on it. It's read-write, so it's not like it's only a view. So that's very important. And it's really a step-by-step evolution. You will define those microservices, add your new greenfield microservices that will literally choke the monolith. And when you're ready, you will actually be able to do the transfer of data and move stuff around for real, but you will have a lot of confidence into what you have done before. So you can get started virtually before going on the physical aspect. Another interesting aspect on that is even on a given microservice is about evolution. So when you got a new version of a microservice, if it's just got its easy, quote unquote, you got your A/B routing, go to the new version, they all talk to the same database. Yes, but what happens when you change the database schema, maybe in a backward compatible fashion? So if you had a virtual layer for V2 that looks at the new shape of the database, you could say, okay, this virtual layer will go to the main database for most of the data, but this extra column or this transform column, maybe I'll got another side physical database on the side to deal with that. And when I'm happy with V2, then I can, merge those two layers. But more importantly, if I'm unhappy about V2, what do I need to do? Well, I remove the code of app V2, I remove the virtual layer, I remove this side database where I don't need the data anymore, and the application is back in business. The second problem is data security. Because you have way more interactions, way more data exposed, you need to think about that a bit more aggressively. Well, I shouldn't have to break the news to you, GDPR, all of that. So we do have some regulatory constraint into who has access to what and auditing and all of that. If I take a subset of the security and data, the questions I like to ask myself is, let's try and restrict the access to really a subset of the data. Let's try to anonymize the data if the specific application doesn't need that information, like the username or the email or something like that. Maybe depending on who is logged, maybe an admin will have more rights and visibility than somebody in an hotel at the counter with, doesn't need to know where the person is living or things like that. And also maybe I want to be able to audit who has access to what, who has updated what, right? And again, we'll use the virtual database in this model to really say, okay, let's all the stream for that, or all the interaction for that application to look at that virtual database. And then I can add security almost like declaratively. I can decide, you know what, do I want to restrict the schema or not? How much? Do I want to add role-based access control on that? So the admin has different rights and visibility on the columns than a regular host. Do I want to log every reads or every writes, push that into something like Elasticsearch to then do auditing and being able to be compliant to the law? All of that without, of course, changing the monolith database, which sometimes is very touchy in an organization. So the benefits is, from the app development point of view, there is no change. You just go and access the database via JDBC, life is good. But there is a tool on top of which you can add and reduce the level of security depending exactly on your need. And what is interesting is that you can share the same technology across the various microservices without the actual microservice team having to really care about that. And that's enough talking, and let's have Madou actually show you some code.
Thank you, Emmanuel. So the demo I'm going to show you in the moment, it's based on a hotel reservation scenario. So the original hotel booking system is a large application with one single database which contains all information, all business logic, all code about booking reservation, customer details, and hotel and room inventory. So the problem is that we need to deal with three main challenges at the same time. The first one is about adding new features, new functionality to our application, and to be compliant with existing and new regulations. The second one is about tight deadlines, because even small changes to a part of the application require many teams to be involved in, and we would like teams to work independently and in parallel. And the third one, and I think it's the most important, it's about customer experience, because we don't want to impact customers when doing maintenance, for example, and we want to adopt zero downtime politics. So, and to fulfill all these requirements, so we set up this microservice architecture. So this is the architecture of the demo, the goal that we want to achieve, and I'm going to explain you step by step how we build it. So first, let's break up the monolith database. So at your left-hand side, you can see the original application with the monolith database, which is defined with a typical data schemas. So a lot of entities linked by IDs, so primary key, foreign key, and so on. So we created a virtual data abstraction layer to break up the monolith database into three virtual databases. So one for each microservices, one for each domain. And each of these microservices expose only the data in the right format needed for the specific domain. For example, for the reservation, we are going to have one virtual aggregating table. For the inventory, we are going to have two. So one for room, the other one for hotel. And for customer, two also. So one that we are going to use for authentication, and the other one that to retrieve more information about customer. But what a virtual database look like? So let's focus on the customer one. So a virtual database in that context is a XML file which contains all definition about the virtual data model that we create. So for the virtual database customer, you are going to retrieve the source model, which means where we are going to retrieve the data, the original data. So it's based on PostgreSQL, and it's our monolith database, of course. And then we define a virtual data model. So here, my layer data service layer, which contain my two tables, so one for customer and one for details. And for example, details, if we look in the definition, it's a three-table join with customer, CT, and information and the payment information, which contains some data transformation like this concatenation. When we add the customer name, the CT name to the address, and some data anonymization, because we only displayed the 4 last digits of the credit card number. So once I create my virtual database, I'm going to deploy them into a data virtualization server running on top of OpenShift. So here it's my OpenShift environment. So my cloud, my container platform, and I have my, will be good. So I have my data virtualization here up and running. So you have to keep in mind that the virtual database acts as a normal and autonomous physical database. So for example, I will be able to access to it through JDBC, ODBC, a kind of data protocol for the data. So for example, here from my SQL client, I'm going to edit the connection. So from the connection, you are going to retrieve the JDBC URL with the name of my VDB, my OpenShift endpoint, and my user password. So I can define a lot of different user passwords for this specific VDB. So once I have my VDB, so when I'm connect to, you are going to see that it really acts as the normal VDB, no difference. As the normal database, sorry, no difference. And under my schema, my virtual model data service layer, I'm going to retrieve my two table, customer and details. And to this virtual database, I'm able to execute any kind of SQL queries as I usually do with a relational database. And you can retrieve here for numbers and address. I retrieve my data transformation and my data anonymization. And then I'm going to use exactly the same protocol in order to connect my microservices to my virtual database. So here, my microservices is based on Spring Boot application. So I'm go back to my project. So my project customers. I'm going to check on if you are familiar with Spring Boot application. So all the configuration are on this application.properties file. And you are going to retrieve the information to access to my data virtualization server. So the driver, which is state, so the JDBC URL and the logging and the password. And now, so my microservices is deployed up and running, and I'm going to do a test with you. So my customer services, I'm using the Swagger UI to make this test. I would like to query the REST resources get details that I'm going to try out. User customer ID. So let's take the customer ID for Avery Brandy. So 424, I execute. And you can see here, so my microservice is up and running and retrieve data from my virtual database. And you can see here the data transformation that I made so virtually. And my monolith database stay as it is. So in this first part, so we demonstrate how easy and how fast we are able to break up virtually a database and how we can consume data exposed by VDBs through microservices without impacting our original application. So now Emmanuel is going to talk about the state in the microservice context.
So we're being told to write stateless applications, but of course there is state somewhere, otherwise the application is pretty useless. So let's try and take a step back and rethink why we are saying we need to write stateless applications. So in a universe where you need to be much more fluid, you need to be able to scale up, scale down. If your application is actually handling the state, like having to each instance, each process of the application to deal with the state, then what happens when you decide to go from V1 to V2? When I kill two of those processes, where does the state go? Is it fully replicated? How do I do that? So it's not necessarily an easy problem. It's called distributed computing, and people have been at it for quite a while. The other problem is you're mixing CPU, the CPU knob with the amount of size, the size or the amount of memory knob, right? And you're bundling those two together. So it's a bit easier when you really say, my application is really focusing on the business aspect and stateless, and I can go from V1 to V2 by just replacing those stateless processes, and it won't have any impact on the user. I can, scale up and scale down. If one goes down for some reason, it's no problem at all. But you need this magical unicorn where the data is magically stored, right? And by state, I don't necessarily mean the state you would have put in a regular database for long-term storage, but anything that is making your application more useful, like, maybe the basket, maybe it's the last n articles that have been seen by a user, because all of those, I'll probably push that information to maybe a machine learning model, a microservice doing that and giving me back recommendations that I will display in an asynchronous fashion to the user, or anything like that. Every time you have been thinking about HTTP sessions, that these are good state for that. So the approach here is to say, okay, let's take a cluster that will deal with the state of the application, so that When I'm writing the application, it's fully stateless, and I can, decide to kill those instances, those containers, replace it with V2, and have no impact whatsoever on it. In this case, we'll go for a data grid. It has a couple of advantages. First of all, it's very low latency because most of the data is kept in memory if we can. The other advantage is if you lose nodes, you don't lose the data, well, up to a certain point. But if you happen to lose a node or scale down, what's happening is that, as you can see, we split the data evenly across the 4 nodes here. In practice, it's a consistent hash map, but here, for simplicity, I've used ranges. But let's say node number 2 dies. Oh my God, I've lost G2L. My users will have a degraded, user experience. Actually, no, because G2L was backed up in node number 1, and when the cluster realized node number 2 is going out without notice, then they reform a 3-node cluster and rebalance the data accordingly. And it's the same logic when you add new nodes to the cluster, then the data is redistributed and you're scaling up and down very nicely for that. And you kept the complexity outside of the app. From an application point of view, it's very much like I'm having a map, I'm putting stuff in a key, and the value is there, and I can retrieve it. Can even get change notifications and things like that. There is another benefit. I don't know if you're in a multi-data center architecture yet or already, but imagine either several data center or several zone availability in a given data center. What happens usually is you say, okay, some of my customers go there, the rest go there, and then you've got your application stateless deployed, and you're having the data grid running on this data center, and let's say it's data center number 1, so all of the users from A to M are actually storing their state there. What happens is the data grid has a replication model where they can connect to another data grid and replicate the state, so that the data center number 2, the state of that is also into the data center number 1, because the data grid has all of the customer information thanks to this synchronization. And yes, it can deal with merge and eventual consistency and having merge policy to recover from those conflicts. But a very interesting pattern that I just recently named the one-way street write patterns is to think about those solutions where you shard the load across different areas to say, okay, I'll do some sort of affinity. All of the user A to M are going to go to data center number 1, which means all of the operations and the state for that specific user will be there. And I will have much less problem with eventual consistency and asynchronous replication and things like that. So that all of the change for the user from A to M will always happen on the data grid number 1 and go down as a write replication to the database number 2. And of course, customer, N to Z are going the other way around, but they don't overlap on the same key. So it's a very nice pattern, avoiding a lot of trouble. Use it for data grids, use it for Kafka, any kind of replicated system that needs to go that way. Caching, I won't spend a lot of time on it, but when you write one application into 20 microservices, some of them might actually be called in sequence, meaning you're adding latency. So the faster you are, the better. And again, we're going to use a key value store model here. There is one big different configuration-wise compared to the one we've seen above. If we lose a node, we lose data, but we don't care. This is a cache. We can recompute that state from maybe the relational database underneath. Okay, so it's going to be a bit slower if I lose the node at the top. Then I'll be slower for G2L until the nodes is back up, and then stuff are being pulled back in as far as the cache being hot. There is another advantage. If you were to put the cache on each of the instances of the application, then your hit-miss ratio would be much worse, right? Because for all of the user, they will randomly go into one of the stateless instances, so the cache would have to have all of the keys for all of the users or the most frequent users at the given time. And the hit-miss ratio per megabyte or gigabyte used is much better. It's much better if you actually say, I'm going to share the cache across all of those stateless instances. And also, if you deploy the application, you're not going to have a cache being going from hot to cold and then having to warming up again. All right, maturing. Yeah, so we've seen how to go from thanks to virtualization to try out the microservices isolation and virtual context. We've seen how to make use of, deal with the state and scalability of the system with something like a distributed key value store. The next step is to go back to these nice islands of microservices. So we've been into that journey, and now we're ready to go a bit further along. So what's interesting with that model is to say, okay, those islands have well-defined bridges with one another. In this case, I'm using data streams, which means I'm able to scale the very specific area I really need to. If I had one monolith, I would have to rewrite my whole monolith to use this new scalable technology, maybe from a relational database to Cassandra. In this case, maybe I realize only application 2 need to scale to a much higher level than I anticipated before. So that's where I will pay the price to rewrite that, but that's a subset of it. So from the data stream, which is essentially the list of change events that happened since quote-unquote the origin of time, I won't go into the details here, pushed by application 1, I will be able to create an application 2, consume those streams, and recreate the state and put that inside, in this case, in-memory data grid where it was on a DB2 instance before. I can run them in parallel for a little while, and once I'm ready to say goodbye to V1, I can do that. The other advantage is to be much more agile as far as consuming your data from a business point of view. I've got the data stream, which is consumed and produced by app 2, which is consumed by app 3. And then, I've got this new idea. It would be awesome to listen to all of the last articles seen by a user to really rebuild and improve our machine learning model every 2 hours instead of every month. And then I'm creating this new application that will listen to the recently article viewed and then do some magic and then, feed that back. So you got a lot of flexibility also from the business point of view. But it is hard, right? You need to have a clear definition between the various islands and to really do it properly. I don't know if you use event sourcing, but it's not easy. I don't know about you, but usually a team going into event sourcing, it's a very long journey, requires a lot of maturation and mistakes, and even events being immutable, it has a lot of complexity and so on and so on. There is some sort of an intermediary state which is interesting, not necessarily at the end goal, but definitely to get started, is to say, okay, event sourcing is really about listening to all changes happening and publishing them so that other people can consume it. And here you can use a system called change data capture, which is not at the business level like true event sourcing is, but more at the what's happening in my database, what's happening with my data. And here the monolith database is actually, we'll listen to the transaction log, put that in a queue, a Kafka queue in this case, so that it's replayable. And by the way, the project is called Devoxx, so it's built on top of Kafka. And from then on, I've got the changes in the Kafka queue from all of the changes that happen in the database, and I can create new application to listen to that, okay, in a flexible way. So what's interesting is that you will not miss one change ever. So imagine you had to do that manually. Your application would have to send those change events, but changing the events in a two-phase commit with the database changes, might or might not be okay for you, or you got the read your own write kind of trouble. In this model, at least you always write to the database, and you will listen to the database as the source of changes, right? And there is no one path in the application you forgot to add the send event code. Everything goes down to the database, you listen to the database changes, and they are published. The other advantage is you can add a lot of stuff behind the database without adding extra load on the database. And also it's much more real time. You could imagine saying every time there is a change in the database, within 200 milliseconds, it's been propagated and those changes are visible to downstream. And that's, again, a lot of talking, and let's move to some demo on that.
Okay. So previously, we were at this stage where we have 3 backend microservices reading data from virtual database, up and running, and ready to be consumed by a front-end application. So now that we have the web application, so let's start to book a room. here. So let's imagine that I'm in the public transport and I would like to start planning my next vacation in Japan, for example. So I'm accessing to the web application. So Red Hat Hotel, our door is always open. And I think that IBM got this message.
What? Nobody tells me anything.
And so I enter my credential. So I need to update the demo to change Yahoo to... Okay. Anyway. So I enter to my application. From the application, as I mentioned, I would like to go to Tokyo from the 19th of November to the end of the month. So I submit here. Okay, so now I have the list of the available hotels. So let's say I would like to this one. I like the name. So Tokyo Sherry Lane. I select this one. Now I have the list of my room. And now I need to stop because I arrived at my train station. And I need to go back home. So I stop there.
There is a no phone policy in your home, I guess.
Yeah. So now what I'm going to do in the meantime, I'm going to kill all my process. So all my three microservices and the web application. So I execute this. Shift. So with this script, it's going to kill everything. So just a moment. Okay. Okay. Sorry for that. The demo effect. Ding dong. Tuk tuk. Dim. Okay, I'm going to kill everything. So as you can see here, so it's just for my customers. Oops. Services, but I'm going to kill all the others.
Trust you, don't worry.
Yeah.
No, we actually kill all of the services, Spring Boot applications in this case.
Yes. And automatically, because it's some feature that I have from my platform, it's going to reboot all my services right forward. Okay. Okay. So just for these two ones, so I kill all my instance. Believe me, I always say the truth. And then let's say that I'm arrived at home. I arrive at home, and I would like to finalize my reservation. So now I'm going to use my web browser. So I'm going to my web application. I access to the web application. Still the same user. I enter my credential. From the credential. So from here, you can see that I have a notification saying that I have a booking in progress. And when I click to summarize, so I'm facing a really great user experience because I'm able to continue my booking where I left, so in the train. So how it's possible? Because I kill all the instance, I kill my web application. So how it's possible? So I think because Emmanuel just talked about this. So all the booking state that I have, it's stored into an in-memory data grid, which means that all my microservices are stateless. And with the in-memory data grid, I'm able to perform and to get some, to allow me to use, for example, the horizontal scalability, which provide me high availability, low latency, and high throughput. So for example, here I just add 3 new nodes to my data grid cluster. But let's go further. Let's say that I would like to test a new version of my application. So what I've got here, so I already deployed my new version of the application, but so far, all my traffic is going to the first version. So what I'm going to do, I'm going to use A/B testing to test this new version of my application. And I'm going to redirect 75% on my traffic to this new version. So it's going to do, think it's 5 seconds. It's going to change it. So now I just switch and do and enable the A/B testing. So let's say from the web UI, I would like not going to Tokyo, but I'll change. I would like to go to Lima in December. Okay, so I submit. From Lima, I would like to go to Lima Park Terrace, for example, and I select this one. And if I go back to my mobile, just to see that there is nothing into my cookie, into my cache, and so on. So I go back to my overview. So on the mobile, I have a booking in progress, which is true. And now you can see a new screen because so now I would like to go to Lima Park Terrace, so in December, and I highlight in green all room with a living area that I have. And after a while, I will be able, for example, to select which one and which version of my application I want to keep in production. And I'm just going to do exactly the same process, because I'm going just to say that everything is going to the new version, because I really like the new version. So I execute this, and here we're going to have the change, and now I'm switched completely into my second version without any downtime. So here in the second part of the demo, what we demonstrate is the fact that we are able to share a state, so between different microservices and different web applications into in-memory data grid. So to give me some capability like so scalability, low latency, and high availability of my data. And also the fact that the same state, we are able to share it between different versions of the same application, and allow me to use some A/B testing principle, for example, and with some out-of-the-box capability of my cloud platform, I'm able to update and upgrade an application without downtime. Okay, so now I will let Emmanuel for the final word of the presentation.
Yeah, so what we've seen is that by carefully designing your approach and using the right pattern, you really make your life as a developer simpler and benefit from all of the pros of the platform. But back to microservice and this journey, don't try, well, you can try, but I would recommend you really look at your monolith application, your monolith database, and do it step by step in an incremental fashion. And this notion of virtual database is actually very interesting to try and test the water, and make sure that you've got the bounded context correctly, the split between your microservices is fine. And then in a second stage, or maybe never actually, you will move actually the data from the monolith away once each of the feature of the monolith has been disabled. Think about security somewhat upfront. Have a chat with your actual security team. I don't know if you guys know who in your company is the security team, but you probably should. This is a subject more and more important. So have an open chat about that. They like beer too. And make sure you delegate the state management outside of your application, so you keep all of the freedom of being able to scale up, scale down, test new versions without having a downtime as far as user experience and making your life more complex. But again, remember, those microservices, especially the data aspect, is really a journey. So take your time and try and use the tools to go one step after the other. And have a look at this change data capture as also a way to test the water as far as event sourcing or booting up this real-time infrastructure or IT that maybe your CTO is dreaming of. What I like about this slide that it shows that the pattern we've been using, so the gray one are really where the data is living, but from the application development point of view, we use a variety of different technologies without any specific impact. We access a database, we just access a key value store with multiple clients, Java, Python, Node.js, and so on. And we use this platform, which gives us a lot of flexibility, which is OpenShift, which is the Kubernetes distribution of Red Hat really. This went fast. We actually had to cut a lot of subjects to really fit within 50 minutes. The actual demo is available on GitHub, so keep an eye on that. And there is a very short book, free book, first of all, and 2 short book. It might actually be at the Red Hat booth. I didn't check. But it's a very nice book onto the patterns to move from a monolith database to a microservice database, a relational database, and how you evolve your schema without breaking the various versions of your monolith. So it's a very easy and good read. And we've got quite a bunch of blogs around these, microservice, how to deal with that, and so on. Christian Posta is one of our evangelists, which is doing a very nice job about that. With that being said, thank you. Please go and vote and give us comments. These were options to try and make you think maybe differently than what you're doing right now. And let's open up for questions to try and see if we can clarify a few things. Yes. Yeah.
Definitely need to think about scalability of the virtual database and performance. There's an extra layer there.
Yeah.
So do you have any?
So the question is, maybe I'll let Madou go into details, but the question is, virtual database doesn't add a scalability trouble and make stuff slower. So the TEED is actually clusterable. First of all, it can get HS, so you can have more than one server on that. And B, we've seen cases where actually having the virtual server in front can actually be faster than going straight to the database because the driver is handling stuff a bit better. It's very anecdotic, but usually the overhead is pretty low. Maybe you can dive a bit more on that.
Yes, because in data virtualization, so we don't copy the data. So each time that we issue a query, so it's going, let's say, to push the query in real time to the underlying database. So about scalability, so you will be able to have a cluster to be able to handle the workload if you have a height workload. But behind that, you will still have the problem with the monolith database because also the relational database, for example, it's let's say better when you have a vertical scalability than the horizontal scalability. So, for example, with data virtualization, there is some caching. So you will be able to combine data virtualization and InfiniSpan in order to get and to cache the data directly into that virtual layer and to avoid to go too much, for example, to the underlying data sources.
For info, there is another mod. Here we use the server because we think the separation of concern is nicer. But there is a mod in TEED where it's literally an embedded JDBC driver, but that is super smart. That is actually doing this delegation. So in this case, there is not even an intermediary hop in your model. Another question? Okay. Well, thank you very much for.
Thank you very much.
Yeah, for attending, and see you around.